Yeah, thank you very much for the introduction. I'm very happy to be here to share with you our latest research on physically accurate virtual representation of advanced glass facades, and it's actually the first in an upcoming series of research on glass virtual prototyping that we are planning to do in the future. So with this research, so this is the next one. Okay. So with this research, we are planning to establish the workflow and the foundations for all upcoming research. So to explore all the possibilities and also limitations when it comes to physical-based representation of the glass. And you will see all the challenges that we are facing now, and what are the methods to achieve higher levels of accuracy with different type of tools. So I guess you all have been involved in a glass selection process and decision making, whether you are architect, engineer, or building owner, client, any type of stakeholders should be involved in a glass selection, because the aesthetical aspects is quite important, not only for architects but for all the buildings and the overall function. So so when it comes to decision making, building engineers have more sophisticated tool when it comes to defining quantitative measurements and having very accurate results. But when it comes to architectural workflow, the aesthetical point of view is quite subjective, and it's very biased, and it's not very reliable in some cases. And with the complex glazing, you face many challenges in how to merge all these aspects and performances, and how to match the architectural vision with the engineering performances. And often it is not how you intended to be. So this is just one of the examples when architects envision something very transparent, but probably due to the energy and optical performance, the glass should be a bit more dark and coated and fritted. So the overall, the intended vision that the glass should be transparent, it's not designed and built in that way. So there is a lot of discrepancy along the way, and we are actually trying to decrease this bias and to increase the reliability of the glass virtual prototyping, involving most advanced tools, and seeing how to improve also other tools to increase this accuracy. Generally, the objectives are to develop the methodology for this physical-based glass virtual prototyping, then to test and validate the methodology across the various purpose CIG tools, then to enable massive expansion and uptake of this physically based process, and then to improve the interactivity and the glass selection by adopting this workflow, and to enable glass and facade optioneering to improve the glass selection. So to improve the number of solutions that you test in order to come up with the best one, or the best possible one. So what are the comparison between virtual prototyping and physical prototyping? There are many different differences between these two processes, and some of them are summarized here. And basically, with virtual prototyping, you have countless scalable glass samples. So it means that as soon as you have the glass specification and spectral curves, you will be able to provide physically accurate glass sample, while in the physical prototyping you are limited to the small, usually A4 glass sample that is usually not laminated and do not present whole glass composition. So there is also a bit of bias when it comes to physical prototyping. And also with virtual, you have countless glass configuration to test. With physical, you need to order specific glass configuration, then you need to wait, and this is the limited number of glass configuration that you can test. Also, in virtual prototyping, you have controllable environment, lighting conditions. With the physical one, you have to wait for lighting conditions to match your perspective and your vision as well. So you have to wait for cloudy conditions, for the sky conditions, etc. Also, you have limited viewing directions when it comes to physical prototyping, because you in most of the cases you produce visual sample and visual mock-up that is quite limited when in terms of size when it compares to the whole buildings, and then you cannot match all the perspectives that you have on the glass facades. Also, virtual prototyping is lower cost, while physical is a high cost. Virtual is a high speed, and physical one is a low speed process. And obviously there are many different advantages of the virtual prototyping, but there is one main obstacle so far, and that is the virtual prototyping was not reliable so far. So when you need reliable results, you usually choose the physical prototyping. And our idea is actually not to replace physical prototyping. It should be there, and it should be used for testing the final mock-up and for approving the facade design and fabrication. But virtual prototyping can speed up this process, glass selection, and facilitates decision making, and ultimately it can improve drastically the glass selection process. So what are the options when it comes to virtual prototyping? We have different applications by the glass manufacturers that uses pre-built buildings to show the glass selection and glass configurations. But it is not how you wanted your buildings to visualize. So there is no possibility to visualize your glass selection on your building. So probably there can be some mismatch between the default building design and your design, and not all glass selections fit all building designs. So the progress actually can be made applying the glass configuration directly on the specific building design. And these are just some of the examples showing, for example, radiance. This is the most common tool in engineering, architectural engineering, to show the accurate representation, but it has its own limits, and I will show later what are the limits of the specific RGB configuration. And the other reference paper that I found, it's very recent, and it's used to visualize the dynamic glazing of the Merck liquid crystal windows, also using radiance. So the number of buildings that are tested in this way are quite limited comparing to the all buildings around the world that are being built. So we think there is a great opportunity to scale up the process and to to extract the best possible workflows to achieve this physical accuracy. Also, one of the best examples in visualizing complex glazing comes from ECLA Digital Ocean. And here, I don't know if you can see that pointer. Okay. I don't know if, yeah, there is a complex glass configuration with etched glass, printed glass, laminated, and it's able to show all the optical effects of the complex glazing using spectral simulation. And I will explain just in a couple of slides. So there are different parts of the design process that you need to follow in order to achieve maximum possible accuracy. And this is when it comes to defining geometry of the glass, because it is not the same if you design it with a simple glazing, a simple glass pane, a simple surface, or if you want to represent the IGUs with laminated, with all possible configuration of the glass in a 3D model. So this graphs here, okay. So this graph here show the 4 different level of details of glass configurations from simple surface model, 2 surface models representing IGU, then 1 volume model, and a couple of volumes representing IGUs and laminated glass. And you will see differences later in the visualization. What are the optical effects that you can achieve with this? So this is where it comes really complicated, and why we perceive different colors and gonio apparent behavior of the coated glass, especially when we have double silver or triple silver coatings, because we have many optical reflections and refractions here with every changing of the medium. So as soon as you introduce a couple of layers of silver, you have plenty of optical rays that can be amplified or that can be cancelled due to the phase shifting because of the very thin configuration that actually is in the range of light wave. So to properly simulate this behavior, you would usually need wave optics models, but fortunately enough, there are some simplifications that ray tracing models also can use to simulate this kind of behavior. But since this kind of effect is quite periodical, and it requires a lot of testing, especially with ellipsometry, to find out the right thickness of the coating, and especially the thickness of the silver within the coating, and that is highly unpractical for the mass use. So we think that modeling with a thin film model wouldn't be practical in the near future. Also, the model for defining reflections greatly affects the visualization. So the reflections presented here in this sphere presents actually different grazing angles, and these angles can be represented via these 2 types of model, being analytical or numerical. Analyticals are obviously much more practical and much faster to implement, while numericals can be more precise, but then it comes with effect in decrease in speed, and we use this model in our analysis. And these slides, this one and the one after, shows two different workflows when it comes to light management and the color management. So basically you have two workflows, and one is being spectral, the other one is RGB, so 3 stimulus value simulations, and there is a big difference between these simulations, and I would like to point out you to remember the position of simulation here, because within the spectral workflows, what you need to define is the source illuminant with all the spectral distribution, and then glass materials with the glass spectra, and then the simulation is done directly on the full spectra of both illuminant and glass material. And what comes as a result of simulation is a raw file containing the values in a x, y, z color space that is converted to the sRGB, so the colors are clipped to fit the triangle of RGB that can be represented on displays via color matching functions. So basically, you have the raw files that you can extract many information from that is not biased and not clipped, and also to represent it on the screen, you need to do the tone mapping, and you need to basically clamp the high dynamic range of the raw file to be presented on the screens that are usually 8-bit of depth. So these are some of the samples that we tested. So this is for uncoated, and you can see here, especially comparing this on the left are thin film models, and on the right are volume models, and you can see the optical distortion of the volume models that are very practical for representing curved glass. So whenever you have curved glass, it is not desirable to use the simple surface models, because they cannot represent all the distortion and the total inner refraction and saturation of the colors, especially at the higher glazing angles. But they can represent, if you have many layers, they can represent multiple reflections, for example. So take a look on the drop in the transmittance and how it reflects to the saturation of the color when you compare low E, double silver, and then triple silver, and then quad silver. So there is a saturation in color and increase in reflectivity of the surfaces. And this is a quite good comparison, having in mind that you can visualize all the energy parameters of the glass and optical parameters, and also side-by-side comparison of the glass visualization. That is quite handy to understand what are the effects of the spectral curves and how they are visualized in actual glass samples. And this is the clear state of the electrochromics, the tinted state of electrochromics, then the same samples just run over the cloudy sky, and there is a different perception of the same glazing. So these samples should be tested under different lighting conditions to get the range of possible color representation of the same glass. Also, this is the RGB workflow that I mentioned. So take a look here at the simulation that comes after the clipping. So you basically lose the information that you sometimes need with complex scenarios, especially when you have some peaks in the source illuminant, if you have mixed lighting, if you have goni apparent coating that can change color depending on the angle. So all these aspects are somehow lost in the RGB workflow. Nevertheless, we still can visualize, but with a lower level of accuracy. But I think within this workflow, the intention is to increase actually the current level of representation and to allow mass adoption of reasonably accurate representation. So this is done by commercial renderer that is most common in the architectural industry. So we expect that this kind of workflow will enable this greater adoption, while specific aspects that cannot be simulated via RGB workflow should be sought in spectral simulation workflows. Yeah, these videos actually show this distortion. If we can go back. Yeah. So you can better see the reflections and distortions by the right hand sample being the volume glass model. And also we tested the workflow on the glass skyscraper by Mies van der Rohe. That is actually the first sample of the glass skyscraper that made a revolution that we see today. And it is actually the perfect example to show all the differences between the transparency, reflections, multiple reflections, self-reflections, self-shadowing on the same building with the same glass. So as you can see, this is the same glass, and the differences in color and can be seen from left to the right, also with a changing environment and dynamic behavior of these reflections. Also testing 3 different glass samples under the same glass conditions. So you can see the wide variety of glass representations and possibilities, this one being a highly reflective glass. Also, we tested it under the full day cycle with a changing lighting environment, with the changing illuminance values, so to show the appearance of the same glass under different lighting levels, showing different transparency and also reflections. Again, for all 3 samples. And this kind of study actually represents the first part in our future work that we are planning to do, and to focus more on different aspects of the workflow, and to focus more on dynamic appearance of the glass, and especially dynamic glass, switchable glass, and how it reflects with the changing environments, and also occupant comfort, because this kind of virtual representation and virtual prototyping gives plenty of possibilities to test number of solutions with the changing environments, and to test solutions for the occupant feedback and response, to validate this switchable glazing behavior, and to understand what is the sweet spot between the frequency of change and the occupant visual comfort. And also the goal is to expand this methodology to other materials and facade systems, such as plastics, BIPV, TFE, media facades, and also to validate the CGI output against the physical samples, because this is the most critical part for the larger adoption, to validate first all these CGI tools with physical samples, and then to validate spectral workflows against RGB workflow. And this is just the map of most important tools in the market currently available, and this is the one that we tested. So we tested ECLA Digital Ocean, that is not only spectral, but it can simulate all the light effects and also light polarization, and it's very highly accurate. And I think the most advanced tool on the market. And then we have different group of tools from the spectral part that use different methodologies to work on the spectral, and some of them used only multi-banded approach that is not fully spectral. And this part here on the left represents the accurate, mostly accurate model. Then we have interactive models that are fast with reasonable accuracy, and then we have real-time tools that are not designed for the accuracy, but for entertainment and for different purposes. And but they are quite fast and interactive, and the market is really demanding this kind of preview. So it will be a challenge to combine the effort to test all these tools and compare and to evaluate the possibilities. And one of the options could be to design the glass materials models via two different file formats, and one being NVIDIA material definition language or open shaded language that will enable one definition that can be applied to many different tools that support this glass configuration. Yeah, that would be all. Thank you. Questions?
Yes, questions from the audience.
Thank you. Thank you for a really interesting presentation and for this work in developing our digital accuracy in respect to the physical world. So my question is related to principally the surfaces on which you're doing this modeling work on, because oftentimes we see perfectly flat elevations being used to conduct this work, and I think, am I right in saying yours was similar to that? Whereas in reality, we see every panel has some bow, some slight curvature, there's pillowing effects, there's steps and misalignments in facade installation. And I think that could make, or does make, quite a big visual impact on how buildings appear. And I was wondering if you considered this, is it part of future work?
Yes, indeed. It is part of the future work, but obviously in the accurate part of the tools, and especially within ECLA Digital. And we are working together, and they are also very experienced in this kind of modeling defects on the glass, especially anisotropy or roller waves, birefringence. This kind of effect can be simulated with ECLA Digital, while other tools are very limited when it comes to this effect. I assume that some kind of effect like roller waves and small deformation and the curvature can be simulated also with these RGB tools as well. Probably not modeling the geometry itself, but using the BAP maps or normal maps to offset the curvature with this kind of black and white maps that informs the renderers about the depth of the glass. And this is not yet tested, but it's all part of the future work. Obviously, the architects do not want to show the defects at first, so I don't see it coming in the architectural workflows, but I see it more applicable to the manufacturer workflow, and possibly also testing, for example, color accuracy for standards. And this kind of virtual prototyping can be useful for this kind of purposes, to visualize whole range of different deflects and defects, and to find the optimal range that is tolerable. So, yeah.
Thank you.
Thanks.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.